Today we're going to dive into something pretty revolutionary, a new way to decode the actual blueprints of our own cells. And I mean, this is the kind of technology that could completely change how we look at disease. It all comes down to a really powerful and surprisingly simple idea.
Just try to wrap your head around this for a second. Your body is built from something like 37 trillion cells. That's an insane number. But here's the thing. It's not just a random pile of cells. It's this incredible, perfectly designed masterpiece of architecture. And for years, scientists have been trying and struggling to read the blueprint for it all. Well, a new breakthrough might mean we can finally do it.
So that's the big question, right? How does this massive construction project actually work? How do all those trillions of cells know exactly where to go, what to connect with, and what to build? Well, that secret, it's all hidden away in our body's architecture.
Okay, so for the longest time, the way we tried to figure this out was, top down. And the best way to think about it is like trying to understand a city just by looking at a really blurry satellite photo. You can kind of make out the neighborhoods, but all the important details, they're just a smudge. This new way, though, completely flips that on its head. It's bottom up. So instead of staring at that blurry city, we're now down on the ground, identifying the actual bricks used to build every single house. And as you can imagine, the picture you get is just so much clearer and more reliable.
Right, so to find these fundamental bricks, these building blocks, researchers needed a totally new kind of tool. Not a physical microscope, but a computational one. And what they built is a really powerful new AI. They call it TrimNN.
Now, TrimNN stands for Triangulation Cellular Community Motif Neural Network. Yeah, I know, it's a mouthful. But that first part, triangulation, is actually the key to the whole thing. The AI basically connects neighboring cells into this massive web of triangles. Why? Because it's a super efficient way to spot recurring patterns in space. Its whole job is to hunt for these tiny repeating groups of cells, those building blocks we've been talking about, which have a fancy name, cellular community motifs.
The whole process is actually pretty straightforward and, honestly, kind of elegant. First, you feed TrimNN a super detailed map. This map shows the exact location and the specific type of every single cell in a tissue sample. Then, the deep learning engine just gets to work, hunting for those recurring patterns, the motifs. And then comes the really cool part, the final step, which is where the magic really happens. That's when we take those patterns and link them to real-world stuff, like how a disease is progressing, and suddenly you've got these incredible new insights.
Okay, so let's get into what these cellular building blocks really are. We've mentioned the term cellular community motifs. Getting a handle on what these are is, no exaggeration, the key to this whole thing.
So a cellular community motif, or CC motif for short, is just a small, repeating pattern of different kinds of cells. And honestly, the absolute best way to think about them is like Legos, right? You've got these simple, standard little bricks, but with them, you can build anything, no matter how complex. TrimNN's job is to figure out what our body's fundamental Lego pieces are.
So let's start with the absolute simplest one, the most basic Lego brick, if you will, a size 2 motif. This is literally just a pair of two different cells that are always found hanging out together, interacting side by side.
Okay, easy enough. Now, from there, we can step it up just a little bit to a size 3 motif. This is just a little trio of cells forming a stable triangle. It's the next level up in how things are organized.
And you can probably see where this is going. These simple pairs and trios, they start to combine, forming larger, more complex motifs with 4, 5, or even more cells. And these bigger structures, these are the ones that really start to define the large-scale architecture of our tissues.
Now, this is all fascinating, but it's way more than just a cool biological puzzle. So what actually happens when you take this Lego building approach and apply it to something really serious, like decoding a complex disease like colorectal cancer?
The results were pretty stunning, actually. When researchers used an older method to try and predict which cancer patients were high risk, they were right about 71% of the time. Not bad. But when they used the size 3 motifs that TrimNN found, that accuracy shot up to 81%. That is a massive jump in medicine. Think about what that means. Doctors could be so much more certain about who needs aggressive treatment, all because of these tiny patterns of cells.
And really, this is the key takeaway. The researchers put it best in their paper, saying that these motifs, they substantially correlate with patient survival. And, this is the important part, which cannot be inferred by other existing tools. So, in plain English, TrimNN is seeing important life-or-death patterns that were just completely invisible to us before.
So what did one of these smoking gun patterns actually look like? Well, one of the most powerful ones they found was a specific size 4 motif. It was like a little neighborhood made up of 2 immune cells, macrophages, and 2 smooth muscle cells. Just that specific arrangement, that specific Lego block, turned out to be incredibly important.
And when I say important, I mean statistically significant. The p-value for this finding was 0.0093. Now, for anyone not deep in statistics, a p-value is just a probability that you'd see this result by pure random chance. So a value that low, less than 1%, that's like flipping a coin and getting heads 7 or 8 times in a row. It tells you with a lot of certainty that this is not a coincidence. This little cellular neighborhood is a real, genuine sign of a much more dangerous version of the cancer.
But this isn't just about cancer. The researchers then wondered, okay, what else can this do? So they pointed TrimNN at the brain to see if it could give us any new clues about a disease as complex as Alzheimer's.
And what it found was incredible. It painted this super detailed picture of the battlefield inside an Alzheimer's-affected brain. It found these distinct cellular neighborhoods that were behaving in totally different ways. For example, you had motifs made up entirely of the brain's immune cells called microglia, and they were all clustered right up against the toxic plaques that are the hallmark of the disease. But then it also found other motifs, these ones made of healthy neurons, that looked like they were actively trying to get away from those same toxic plaques.
So you've got these two completely different stories happening at the exact same time. On one side, you've got the immune cells rushing in towards the damage, right? They're forming this inflammatory front line. But on the other side, you've got the healthy neurons retreating, pulling away from the danger. We're literally seeing attack and retreat on a microscopic scale. That's a dynamic that was almost impossible to see clearly before this.
So what's the big picture here? The crucial point is that we're moving away from a blurry, kind of generalized understanding of our tissues and towards a super sharp, high-resolution map that's built from these fundamental Lego bricks.
And the advantage of doing it this way is just huge. I mean, instead of these abstract blobs of data, we have actual, countable, visual building blocks that you can actually understand. The results are more stable. They're less likely to be thrown off by noise in the data. And of course, the big one, they lead to way better predictions about disease. It really is a completely new angle for understanding the microscopic world that's going on inside all of us.
And all of this brings us to a pretty profound question. We are really just at the very beginning of learning how to speak this new cellular language. So now that we finally have a tool that can read our body's architectural blueprints, the question isn't if we can decode disease anymore. The question is, which one should we decode next? I mean, from autoimmune disorders to the mysteries of aging itself, the possibilities are just staggering.